Hello everyone, this is a tutorial for Lark version 3. Lark Spectral Lighting is based on Lark Spectral Lighting version 1 and 2 for Grasshopper and Rhino environment to investigate non-visual light. Lark was originally developed as a collaboration between University of Washington and ZGF Architects, and Lark version 2 was developed by EPFL, Oregon State University, and Eindhoven University of Technology. And Lark version 3 was developed by University of Washington and ZGF Architects. So when you open the script, so once you download the zip file from Food for Rhino, there will be this folder example files, which will have two folders. One will be point in time and the other will be time series. The time series will have a Rhino file, a Grasshopper file, and simulation inputs folder. And all of this is coming directly from Lark version 2. So you can look at the time series tutorial from Lark version 2 on the YouTube. And then there is this point in time folder, which is the updated version for Lark version 3. So once you open this sample room, patient room, this is what you're going to see, which is basically a patient room that is a sample room that we're going to use that has an east-facing window, and this view is looking towards that window. And then when you open the Grasshopper file, this is what you're going to see. So this script, you are going to work through from left to right. So on the far left, you're going to prepare the things that is going to be needed to run the simulation. And then in this part, which is SPD processing, so spectral power distribution processing, you are going to simplify the spectral power distribution information that you're going to feed in the prep step into 3-channel or 9-channel Radiance files. And then you're going to use this information to simulate either to 3-channel or 9-channel. And then this 3-channel and 9-channel information is post-processed into the non-visual lighting metrics. In the 3-channel, the lighting metrics will include photopic and melanopic light, and then in the 9-channel, it will include photopic, melanopic, and neuropic light. The neuropic light is the additional component which was added in version 3. So we will go through these steps together. For the 3-channel, we will go through the image-based simulation with electric lights. And then for the 9-channel simulation, we will go through both the image and the point-based simulation without electric lights. So on the far left, there is this toggles area where you will see a honeybee component, which is a false start toggle. So if you're going to run the simulation, you're going to double click this to start the simulation. So one thing that is different in Lark version 3 compared to Lark version 1 and 2 is that we are using this honeybee component, which is here, to just write the RAD file. So in Lark version 1 and 2, the honeybee component was used to write and run the simulation. But in Lark version 3, we are using that component only to write the RAD files. And then there's a new component, which is this component, to run the simulation. So you will need to first write the RAD files and then run the simulation. So first, going into the 3-channel image-based simulation, you need to go through these prep steps. So in the first basic setup area, you can see these yellow panes and then white panes. The yellow panes are basically all the inputs that you're going to put in to run the simulation. And anything that's white is things that is going to be output from what you've put in. So you are going to have to put in a save directory. By default, it's clark and temp. And then you will name the simulations. So I will name it as test 3C image, since we're doing a 3-channel image simulation. And then you will choose the simulation type. So 0 is grid, which is point-based simulation, and then 2 is image-based simulation. So I will keep it to 2. And then you will also choose simulation channel. So 0 will be 3-channel and 1 will be 9. I will change it to 3-channel since we're doing 3-channel image-based simulation. And what is updated in Lark version 3 is how you create the colored sky. So for 3-channel simulation, you have 2 options. One is to use spectra-based Perez sky, which is an update from Lark version 1 and 2, where you can put in spectral power distribution for both sky and the sun. So sun is the new component in version 3. And then the second option is to use luminance-based Perez sky, which colors the sky based on the luminance over the sky dome. And this, you can check more about it in this GenDaylit page where they show this -C option, which is a colored sky model from Aisha Daikite TU Berlin. So for the 3-channel simulation, I will just use Perez spectra-based sky. And then you can also choose the light sources in the scene. So you can either choose to have just a light or electric light or combination of both. And in this case, I'm going to use both of them. And in the basic setup, the last thing that you're going to put is simulation parameters. And I am going to go with the lower settings, which is shown here. So the next thing is to have set up for the grid or image. So since we're doing an image setup, you will be focusing on this area. So this is a view selector. So in the Rhino pane, you will have these views. In my case, I have room, grid, room, right. And then this Python component reads what kind of views you have on your Rhino. And you can choose which of these views that you want to simulate. And I am going to simulate the room. And so it's number 0, and make sure in Rhino that in that pane, it's the view that you want to simulate. So don't zoom out, don't zoom in, make sure it's the view that you want to simulate. And then you will also set up the image pixel resolution and the camera type. In my case, I kept it to 10,000 pixel resolution, and then kept it to a fisheye view, which is 1. You can choose other camera types, but I am keeping it to fisheye view. And then you can also set up a grid sensor based on what type of simulation you're doing. So if you're doing a point-based simulation, you can go through this step. I will go through it now very briefly, although we're not doing it right now. So you have 2 options. One is to use individual sensors, and 2 is to use sensor grid. So individual sensors is you put in a point and then another point to have a vector direction of which view you're looking at. And you can put that in, which will feed into this and this. So you will have a point and a vector to simulate for. in my case, in a later part of the tutorial, we will go through 9-channel point-based simulation, but we will do that through grid. So for the grid simulation, you will need to put in a surface, which will create a grid. And then you will also need to put in the sensor spacing and the number of directions. So the number of directions, we will go through this later in the tutorial in more detail, is basically on a point, you will see how many numbers of directions you want to simulate to. And then this is the unit, which is showing the distance from the floor. And this will always be in the Rhino unit. In my case, the Rhino unit is in feet, so I had to change it to meters since meters is by default used in Honeybee. So after you set up either the image or the grid, you will also set up light sources. So since this is a point-based simulation, point-in-time simulation, you will put in what point in time you're going to study. In my case, I am using June 21st at 12 p.m. And then you will also need to put in a EPW file for the weather information. In my case, I was using Seattle for the location. And then this, when you put it in, it will feed in to this part of the script, which is basically reading the EPW file to give you the location information, which has the latitude, longitude, the time zone, and then radiation information, which includes direct normal radiation, diffuse horizontal radiation, global horizontal radiation. And all of this is basically used to create a sky file information that is used in GenDayLit. So if you look at this page, it'll tell you these options to use to create the GenDayLit sky file. So -W option, you need direct normal irradiance and diffuse horizontal irradiance, or -E option, where you only put in the global horizontal irradiance. So you either have the option to use the EPW file to generate this, or you can put in your own measured data, for example. And if you do that, if you want to put in your own data, you want to overwrite the EPW file. So you turn this to true, which is what I'm doing in my case. And this is also new in version 3 of Lark. So in the previous versions, you could only use the -W option where you give in the direct and diffuse irradiance, but I've updated it so that you can also put in global irradiance as well, which is the -E option in GenDayLit, which is what I'm going to use. And then since we're going to overwrite the EPW file, you need to put in directly what the direct normal irradiance is and the diffuse horizontal irradiance is, or global horizontal irradiance, depending on whether you're using the -W option or the -E option of GenDayLit. And then obviously, yeah, you need to put in other information, which has latitude, longitude, and the time zone. And then last thing that you want to put in to create the sky file, if you're using the Perez Spectral Sky option, which is what you chose here. So you said, I will use Perez Spectral Sky based simulation. You need to put in a spectra of the sky. So here you have the option to put in spectra of the sky and then spectra of the sun. So by default, I've put in D65 for the spectra of the sky, and then ASTM for the spectra of the sun. And then if you're going to use electric lights, you have this option to put in information for the electric lights. So this is where you put in a path to save the colored IES files. And by default, that is set to see Lark luminaires. And then since the electric files will have spectral information and you will name that electric spectral information, I've named it as BIOS 3500. And then you will also put in the spectral power distribution of the electric light source. So this is a Python component that is reading that text file. So you can see that it has information from 380 nanometers to 780 nanometers, showing what kind of spectral power distribution that this electric light is going to have. And then for each of the IES files, in my case, I had 3. So I have IES type 1, 2, and 3. You will put in where that IES file is here, and then the name of the IES file. You will also put in the orientation angle, light loss factor, spin angle, tilt angle, and then you will put in a point in Rhino and then put it here of where that IES file will be. So I've put that in for 3 different IES files. And then the last thing that you will do to set up your script is this material setup. So this material setup, you are putting in spectral information for the materials that will be put into the geometry that will be simulated in Radiance. And you will choose either the material type as 0 for glass or 1 for plastic. And then this is the file path that you will put in for the actual spectral power distribution. And then you will put in the roughness of the material and specularity of the material. You will also put in the geometry of what that material is going to, the geometry of the material, and then you will also put in the name of the material. So what was updated in Lark version 3 is that this component, which is Lark Convert SPD, is that whatever spectral power distribution input text file or CSV file that you're going to put in, it's going to automatically read what the interval will be. So for example, if you put in a text file that has 10 nanometer intervals, so it goes from 380, 390, it will automatically read that interval. And then you will put in the material name, roughness, specularity, material type, channel type, which is what you were putting it in here. So in my case, I had materials for glazing and different colored walls, and then flooring, ceiling, some furniture and ground. And then all of this connects to these components. So this component is basically reading that spectral information and then changing it into a simplified version of color information into 3 channels. So it'll have R, G, and B, or 9 channel information, which will have R1, R2, R3, B1, B2, B3, G1, G2, G3, and so on. So once you put in that prep information, this is the bit where it's changing that spectral power distribution into more simplified version that Radiance will be using to simulate. So we already went through a bit of this. So this is what is reading the EPW file. So which is giving you information that needs to be fed in to create the sky file. So what is different in Lark version 3 is that the component that creates the sky file is not writing the sky file automatically. So basically, it will overwrite whatever the honeybee component is using as a default sky. So the honeybee component will have a non-colored sky, and then later on in the script, which is in this area, it will rewrite the sky file. And this rewriting of the sky file happens based on whatever you put into this component. So you either put in, you either choose to use a spectral Perez sky or the luminance based Perez sky, which is what you were choosing here. So here you were using either spectra-based or luminance-based. In my case, I was using spectra-based. And you need to put in the sky color and the sun color, which is basically coming in from the spectral power distribution information that you put into here. So this was the sky color and this was the sun color. And these two text files will have information such as this. And then it will be simplified into a 3-channel or 9-channel information with these components. So let me just unlock this so we can see what this looks like. So you can see that spectral power information has been simplified into a 3-channel information representing blue, green, and red for the sky and the sun. And this gets fed into this component, where you put in the sky color and the sun color, and then you can either choose to use a -W option or the -E option, and then you will put in the irradiance values. So this component creates a sky file. So for example, if you look at this panel, you can see what the sky file will look like. So it has, it's using GenDaylit, and then it has color for the sun as well as color for the sky. So this information is basically showing a text file. In previous version of Lark, this was showing location of the sky file where it had been overwritten. But in Lark version 3, this overwriting happens after you've run the Radiance, the Honeybee Radiance component, which happens here. So we went through the sky, and then this is where spectra information for the electric light is simplified into 3 or 9 channel. And then this is where spectral information for the material happens. So you can see, for example, a glazing has a material that looks like this, which will be fed into Radiance material files. So all of that is what is used to put into the Radiance simulation. So you will need to put in the sky, you will need to put in the geometry, and then this is just naming the folder, and then this is creating the electric lights that will be fed in to the image-based simulation. So since we're running the image-based simulation, we'll be using this component to write the RAD files. And if you're using a point-based simulation, you'll be using this component instead. So to run the simulation, you need to go back to the far left. So in the far left, this is the toggles. So since we're using a 3-channel image-based simulation with electric lights, you want to rewrite the luminaire files. So I'm going to turn this to true. And you can check that it has created Luminaire files in this Lark Luminaires IES files. And then, so you will also need to write the RAD files. So right now, if you go to Lark temp, it will have created this test3c image, but it will be empty since you haven't written any of the RAD files. So I will turn this to true. It will freeze for a bit. And once it's written the RAD files, you can check in this folder that it has created a folder called 3C. And then inside it will have image-based simulation, and it will have written the files that is coming from the Honeybee component, which has the batch files, the sky file, the material file, and the geometry file. So after that, you will also simulate. So once you click this, it'll go through these batch files to create the HDR image from the simulation. So I will click this. Okay, so the simulation has finished running, and you can check that it has finished running. So since this is the component that is running the simulation, if you look at this, it'll show the location of the HDR file. And you can also check in this folder that it has created the HDR file. And to look at the non-visual effects of lighting, to look at either the illuminance or the luminance values of the scene, you will need to post-process the results, which is going to happen here. So this is the component that will post-process the results into either the photopic luminance or illuminance, or the melanopic luminance or illuminance. So the 3-channel component will not have the neuropic output, as it will lead to inaccurate results from oversimplifying the spectral characteristic in the blue channel. So to turn this, to use this component, you need to turn the toggle to true here, which is going to post-process the results. So I'm going to click that. And once it has finished, you can see that it has created this image for the photopic luminance and this image for the melanopic luminance. And you can see that the electric files have come in with these electric images. And then if you want to analyze this further, you can use, for example, Honeybee false color components such as this to analyze it further. And then this is the component which has field of directional weighing, which is basically based on recent literature, which says different parts of the field of view should get different weighing factors. So if you use this, you will be able to see an image that has different weighing factors applied. And this is basically coming from the Lark version 2 component, so you can look at that tutorial for more information. And then these parts of the script is basically looking at photopic and melanopic illuminances. So if you have a grid simulation, these will have grid information, and then you can use these to preview the results, that is, between the criteria that you set up. We will go through more detail about point-based simulation in a bit. So we finished the 3-channel simulation for the image-based run, and we will go through the 9-channel simulation. So basically, 9-channel simulation is a more accurate simulation, which is dividing the RGB channels further into 9 channels. So R channel will have R1, R2, and R3, and then B channel will be having B1, B2, and B3, and then green channel will be having green 1, green 2, and green 3, which is what is happening here. So this will be representing the blue channel, this will be the green channel, and then this is the red channel. So it will be more accurate simulation. And then the results will be shown for here. So this is the image-based simulation results that you will be looking at, and then this will be the point-based simulation. So I'm going to lock it for now. So in the basic setup, I will change the name into test 9C image. And then simulation type, it'll still be image, and simulation channel type, it will be 1 since it'll be 9 channel. I will still use the spectral sky, and then in the light source, I will only have daylight, and I'll keep the simulation parameters the same. Image setup will be the same, the light source will be the same, and the material will be the same. So in the simulation toggles, I will turn all of these to false. And then I will write the rad files. So once I unlock this, it'll freeze for a moment. So it has written the files in this temp. So you can see it's created this folder, test9c image, which is what we named it. And then it will have created these 3 folders, which will have rad files and the batch files, which will be used for the simulation. So if you go in here, it'll have these batch files and the rad files. And then I will start the simulation. Okay, so it stopped, it finished the simulation, and you can check that it has run the simulation by going here and checking that in the image simulation, it has this directory of where the HDR image is set up. So this blue channel, green channel, and red channel information will get fed into this component, which will post-process the results into photopic, melanopic, and neuropic luminance or illuminance. And to run this, you need to turn this toggle to true. Okay, so it's finished the post-processing. So once you come to this area of the script, you can see that the image has been post-processed into photopic image, melanopic image, and neuropic image. And of course, you can use the false color component to analyze this further. And then again, these are components that is coming from Lark version 2. So you can learn more about it from Lark version 2 tutorial. And then these components are basically from the HDR image, it'll read the Radiance and then apply the alpha OPIC framework developed by the CIE. And then it will output alpha OPIC irradiance, alpha OPIC ELR, alpha OPIC EDI, and then from the irradiance, it will output a 9-channel step function of that image. And then you can also save that into a CSV file with this. So we finished the 9-channel image simulation as well, and then we can go to the 9-channel point-based simulation. So I will lock the script. And then in the basic setup, I will change this to test 9C point. And then simulation type will be grid, so 0. I will keep the simulation channel as 9 channel. have the same type of sky, have daylight source as the light source, and then all of these will be the same. And then let's go through the grid setup. So in the grid, as I was explaining previously, let's go to the Rhino. So in the grid, this is the grid that we're going to create the points. So this will be the surface that is going to go here. And then I will decide to have 8 number of directions. So you can preview the points and the vector directions that you want to analyze by previewing this. So if I unlock this, it will freeze for a moment. Okay, so it has finished it took a long time because I forgot to turn these toggles off. So basically it has run the simulation. But just to show you what these components are doing, it's basically putting in a surface and then it creates these points on that surface. And then because we put in the vector direction as 8, it created 8 vectors for each of the points. And if you put just one, it will have 1 direction. And if you have 2, it'll have 2, and then 3, and so on. So if since the simulation has finished, and you can check that the simulation has finished by going here and looking at the point-based results. It'll show this .res file, and you can also double check that here, and then temp, it'll create this folder test9c point, and then each of these folders will have .res file, which is the result file. And that result files will feed into this component, which will post-process the results into photopic, melanopic, and neuropic illuminance, which will feed into here. So these are showing photopic illuminance for each of the points and vectors for each of the points. So you can preview the results by previewing this. And basically for the photopic, I put a lower threshold of 250 lux and upper threshold of 3000 lux. So any points that is in between these criteria will show up with if you preview this. And I've put in a color range of going from blue to red. And then anything that is lower than 250 lux will show up as black. So if you preview both of these and then go to the Rhino pane, you can see that the most of the points that is looking towards the window will fall in the criteria of 250 lux and 3000 lux. But most of the points that is looking away from the window, even though it is near the window, it will not fall in that criteria. And then you can preview this with melanopic results as well. So if you change these opic results to melanopic, you can check how it changes in the Rhino page as well. And then you can also double check what it looks like for the neuropic, which will be shown in pink. So you can change the type of materials, the geometry and orientation and so on to test what type of design decisions affects the non-visual lights. And then also, if you want to preview the illuminance values, you can preview this. It will slow down the page depending on how many points that you simulated. And since I have several points and then 8 directions, it'll take some time to preview it. So I'm not going to preview that now. And then these are also components coming from Lark version 2. So this is the Alpha Optic framework developed by the CIA, and it'll show the radiance values for all the sensors here. And then it will show a step function representing 9 channels. And this is a step function representing 9 channels for all the points and all the vectors. And you can save this as a CSV file here. And you can change what kind of OPIC that you want to look at. You can choose to go to SML, cone, and red OPIC as well to preview the results. And then this component is previewing the results for whatever OPIC that you choose. And then you can look at it with the vectors. So you can preview this and this to look at the actual illuminance values or the vectors.